In this video, we're going to look at how to write exponential functions and solve some problems involving them. So first off, exponential functions, here's the standard form of the function. So f of x is just equal to a times b to the x, where a here is the initial value. So your initial value can't be 0. But that would be the initial amount of whatever you have. And then b is your base, and b has to be greater than 0. So your exponential base cannot be a negative number. So if you see a negative, it goes with this initial value. So b has to be greater than 0. If b is between 0 and 1, okay, so it can't actually be 0 and it can't actually be 1. If it's between 0 and 1, then it's a decaying function. And if it's greater than 1, then it's a growth function. So it's considered an exponential growth function. And we could probably add here that b actually can't be equal to 1 either, because 1 to any power is just 1. So that would be a constant function. So let's take a look at the function, the exponential function y equals 2 to the x power. So we see that we have the base here of 2, and then here's the graph of that. And so let's fill out the table. So we're just going to fill in 2 to these different powers. So we have 2 to the negative 2, which is 1 over 2 squared, or 1/4. We have 2 to the negative 1, which is 1 over 2 to the first, or 1/2. 2 to the 0, which is 1. 2 to the 1, which is just 2. And 2 to the second, which is just 4. So then we can see those plotted here. So at negative 2, it's at 1/4. At negative 1, it's at 1/2. At 0, we're at 1. At 1, we're at 2. And at 2, we're at 4. And then you could keep that pattern going. So the domain here, so what x values are covered? So we see an arrow going to the left, and we see an arrow going to the right. So you can plug in all real numbers into this domain, and we see that happening here with negatives we can plug in, and positives we can plug in. And then our range, we actually have a lower boundary here. So we have this horizontal asymptote here of y equals 0. So our range cannot ever get to 0, because if we just keep putting in more and more negative numbers, like if we look at negative 100 plugging into this table, it would be 2 to the negative, it would be 1 over 2 to the 100th. Okay, so it'd be 1 over 2 to the positive 100th, which is a huge number on the bottom there. So 1 divided by that huge number is basically 0, but not technically. So the range is going to go for anything higher than 0. So it's never actually going to equal 0, but 0 to infinity. And then it is bounded below at y equals 0. So there's that boundary underneath it. So it's considered bounded below at the line y equals 0, which is our horizontal asymptote, or our end behavior asymptote. Now, the y-intercept, remember, is where we plug 0 in for x, because that's where it crosses this y-axis. So here's our y-intercept at 0, 1, just where you plug in x equals 0. And then our x-intercept is where the function equals 0. And we actually know that that's never going to happen because the range doesn't include 0. So there are no x-intercepts here. It never crosses the x-axis. Then we want to determine whether each exponential function is growth or decay, and then describe the transformations. So this is going to have to do with the base here. So remember, if this base is between 0 and 1, then it's going to be decay. And then if it is greater than 1, it's going to be growth. So in this case, our base is 2. So this is going to be an exponential growth function. For this one, our base is 1/2, so this is going to be a decay function. For this one, our base is 2, so that's growth again. And then here we have 2 also, so this one is growth. So then let's describe the transformations. So in this first one, we see it's got the same base as the parent function, and then it's got a -1 up here inside of the function. So that's going to be a number that impacts the domain. So this is going to be a horizontal shift. And then remember, anytime that it's impacting the domain, it does the opposite of what it looks like. So this is going to be a horizontal shift to the right 1 unit. This next one, we actually need to get the base to match this so that we can see what it's doing for the transformation. So remember that 1/2 is really 1/2 to the first power. So this is like a 2 to the -1 power inside of here. And then that's to the x. So then we really have 2 to the -x. So this one is multiplying by a negative. So it's really kind of the same as this one, except for that we've got that decay happening. But so for this one, it's going to be it's going to impact the domain again, but this time it's going to be a reflection over that axis. So it's going to flip it left to right. Okay, so it's going to be a reflection over the y-axis. Then this next one is just 2 to the -x. So this one is also going to be a reflection over the y-axis. Then this last one is going to have a multiplication. So we've got a stretch, and this is outside of the function. Okay, so this is going to be a vertical stretch, meaning that it's going to impact the range. So vertical stretch by a factor of 3. And then this +7 on the outside here is going to be a vertical shift. Okay, so it's just going to move everything up. So vertical shift 7 units up, or up 7 units. All right, then this next slide is just talking about Euler's number. In case you don't know this number, it's a number that's in your calculator. So you're going to see this when you're using exponential functions a lot. So I just want you to know that this is an actual number, not a variable. So just like when you see pi, we know that pi is 3.14159 ... and it keeps going and it never repeats and it never ends. That's a very similar thing to E. So this is how you define E, how mathematicians define it. And what it does is it gives this number. Okay, so E is approximately 2.71826. And that's just in your calculator. So if you look at your calculator, you'll find the number E here right above the division sign. So if I pushed second divide, it would give me E. I could push enter, and there's that number. Okay, so E is a number, not a variable. All right, then as we write exponential growth and decay function, so this is kind of the simplified version, this a times b to the x. So when we're talking about growth rates, you'll sometimes see it more like this. And so this p sub 0, or it's said p naught, like p naught, that's your initial amount. So that's still the initial amount. The number multiplied outside the parentheses is your initial amount. And then this whole number in here, this 1 plus r, this is your growth factor. This is the same as the b. And then inside of that growth factor, we see this R, which is our growth rate. Okay, so within the growth factor is the growth rate, and it's how much higher or lower this number is than 1. So we're adding the rate to it. So if we have a rate increase, then that's going to be adding. And if we have a rate decrease, then that's going to be subtracting. And then T is just your time, just your variable. So let's go ahead and look at some of these. So you can see that these have been simplified. So it doesn't say 1 plus R in here. So remember that our initial value is still just that front number, right? So either we're thinking of it as A or P sub 0, P naught. The growth factor is that whole 1 plus R. And then the growth rate is just the R value, okay? So we have to figure that out based on this 1 plus R. So in this first one, our initial value is 3, okay? And in this second one, our initial value is 2,500. So now when we go ahead and look at the growth factor, that's this whole number in here. So the growth factor is 1.2 in this one. The growth factor in this one is 0.89. So now we have to figure out the rate. So remember that the rate is just the R. So this number in here, this 1.2, is equal to 1 plus R. So this number, you can set up an equation if you want to. So you can say 1.2 is equal to 1 plus R, and then solve for R. So you're just subtracting 1. So now we're getting 0.2 is our growth rate. And often when we write rate, so you could say R equals 0.2, but when we say the rate, we often say it as a percent. Okay, so the growth rate, if it's 0.2, you multiply by 100 to get your percent. So then this is 20%. So it's an increase or a growth rate of 20%, plus 20%. So over here, this 0.89 is our 1 plus R. So now we have 0.89 equals 1 plus R. So when we subtract 1, we're going to get negative 0.11 as our R. So this means that our rate is decreasing. So we're decreasing. So our rate is negative 0.11, or as a percent, okay, that's negative 11%, or a decrease of 11%. All right, then let's solve a couple problems with this. So a new car is purchased for $2,700. The value of the car depreciates at 13.75% per year. So what will the value of the car be to the nearest cent after 12 years? So we have this initial value here. So here's like our P naught or our A. They're also giving us our rate of decrease. So it's depreciating at 13.75%. So our rate, 13.75%. Remember, when we plug this into our equation, we're going to need the decimal. So we're going to need to divide by 100. So 0.1375 will be what we actually plug in. So our equation is P equals P naught times 1 minus R in this case, since we're decreasing, and then to the T. So our value of our car is going to equal $20,700 times 1 minus this rate, and then to the T. And so our rate here is 0.1375. And so I'm just going to write the equation first, then I'll actually plug that value in. So here we're getting 20,700, and then we'll do 1 minus that rate. And so 1 minus 0.1375 gives us a growth factor of 0.8625. So really what that's saying is it keeps 86.25% of its value each year. So it's losing 13.75% of its value. It's keeping 86.25% of its value. So now we just need to plug in 12 into our time here, and that will give us what our car is worth after 12 years. So if we just go to our calculator, so we'll type in 20,700 times 0.8625 and then to the 12th power. And so this is 3,508. And then we want to round to the nearest cent. So 0.16, because that next one is a 1. So the value of our car after 12 years is $3,508.16. All right, then let's practice one more graphing problem here that's a little bit more, has a couple more transformations. So let's do the table first. And so I want to plug in a couple negative numbers and a couple positive numbers here. So let's do like -2, -1, 0, 1, 2. And so we'll just plug it in here. And if you need some more space, you can always write it in the margins. So we've got 2 times 3 to the -2 plus 1. So then this is 2 times 1 over 3 squared, or 1/9 plus 1. So this is 2/9 plus 1. And so if you want to do that as a decimal, 2/9 is 0.2 repeating plus 1 is 1.222. So this is 1.2 repeating. So then we would do plug in -1. So if we plug in -1, so if I just change this to -1, then that's going to be 2 times 1/3 this time, okay, which is going to be 2/3. So when I multiply this, I'll get 2/3 plus 1. And 2/3 as a decimal is 0.6 repeating. So 2/3 plus 1 is 0.6 repeating. So this one will be 1.6. So if we go to -2, we were at 1.2. And then at -1, we're at 1.6. So then we could plug in 0. So then that's just going to change this stuff. So if I plug in 0, 3 to the 0 is 1. 2 times 1 is 2. And then 2 plus 1 is 3. So at 0, we'll be at 3. Then I can plug in 1. So 3 to the first is 3. 3 times 2 is 6. 6 plus 1 is 7. And that's going to be off my paper. So I'm just going to not plug in the 2. So at 1, we were at 1, 2, 3, 4, 5, 6. So just off the paper. And then you can kind of see that it's looking like this. And so if you remember our original problem that we looked at, okay, we had this horizontal asymptote at y equals 0. Well, in this one, we have this plus 1 on the outside here. So this shifted everything up. So now our horizontal asymptote is at y equals 1 instead of y equals 0. Then we have that y-intercept. Okay, so where we plugged 0 in for x, so our y-intercept is at 0, 3. There is still no x-intercept because our horizontal asymptote moved up to 1, and we can see it's not going to go below that, and it's not crossing that x-axis. Our domain is still all real numbers. We can plug in negatives, we can plug in positives, but now our range moved up to 1 to infinity. So now we're at this 1 to infinity. And then transformations. So we had this 2 out front here, so 2 times. So we had a vertical stretch by a factor of 2. Since it was outside the function, it's impacting the range vertically. And then we had a vertical shift up 1. from this 1 on the outside here.